right, class, we went through how to find a chi-squared goodness of fit. Now this is a test for counted data when we're trying to figure out if our observations match what we previously held to be true. Now these are both problems that we did in class. However, I have a feeling you might have forgotten, or maybe we were moving a little bit quick with our time constraints. So this first problem is dealing with a Mythbusters situation. And in here, we're trying to determine whether or not, and if we look here, it says we're trying to determine if the myth holds true. And that is that the bathroom stall closest to the entrance is used least often and contains the least amount of bacteria. So that's what we're looking for. One of the first things that you should probably do is set up your null and alternative hypothesis. So my null hypothesis here is that the what we'll call it bathroom stall usage is consistent or is equal across the 4 stalls, indicating that they are all equally used and all have equal amounts of bacteria. All have equal amounts of bacteria. Now, in all bacteria, left out to C. Bacteria. Now, in all honesty, the main part of this that we're looking for here is this guy right here. I threw in the final part basically so that I remember what the question is actually asking. It's not asking if the bathroom stall usage was equal. It's talking about the fact that they were all equally used and have equal amounts of bacteria. We can only test this part. So our alternative hypothesis, and this is the easy part, if we have our null, our alternative just simply sticks the word not in there. So our alternative hypothesis is going to be that bathroom stall usage is. All right, now in class we talked about our goodness of fit, and we had to move a little bit quickly through that due to time constraints, due to our testing. So I wanted to take a moment and give you guys an opportunity to go back through it again, see all of the steps, so that you can clearly understand what you were expected to show for an entire chi-squared test and its interpretation. So the first problem that we have here, this was our Mythbusters problem, where we're trying to study this urban myth. So that's what we want to do. We want to test this theory that in a public restroom, the bathroom stall closest to the entrance is used the least often and contains the least amount of bacteria. Now, what we're trying to do here is we can't actually test, or we're not looking at the amounts of bacteria. We're looking at that beginning part. The bathroom stall closest to the entrance is used least often. Well, the only place that we can deal with our tests here when we're talking about counted data is looking at the distribution of that data itself. And remember, a null hypothesis is basically that there is no change. Our null hypothesis should be here, that bathroom stall usage is consistent across the 4 stalls. Our alternative hypothesis is that bathroom stall usage is not consistent across the 4 stalls. So that's always your first step, because depending upon what you are dealing with, you need to make sure that you can pick the right test, and therefore the assumptions and conditions need to be correct. So because I have picked this idea that the distribution itself should be consistent, should have a good fit, that tells me that I'm doing a goodness of fit test. And for my goodness of fit test, the assumptions and conditions are as follows. The first piece that we need, which is probably the most critical, is that the data is counted. And what we are counting here, and it's always good to incorporate exactly what your counts represent, is the number of people using each stall. The second one should really be that the data itself is independent. And hopefully it is. I mean, I've been to a public restroom before, and no, that's not necessarily the case, but we're going to claim that stall usage is independent from person to person. We cannot say that this was randomly selected or randomly collected data, but we hope our data is representative of all stall usage, of all bathroom stall usage. Okay, there's no way that we can be random about this. These people were we recorded people that entered a public restroom and saw what they did. Hopefully not seeing too much. All right, the last one is our counted data assumption. And this was that the expected cell counts are all greater than 5. Now, I put some stars next to this because right now I'm not at a place where I can tell just by looking at this to be able to state it. So our assumptions and conditions and all of our work actually includes the use of a table. So that's what I'm going to do next. I'm going to set up my table. So when I set up my table, I start with this idea of expected counts, observed counts, and my components. Now each of these match for a specific restroom. So I'm going to number my stalls here. 1, 2, 3, 4. Okay. Now I know what my observed counts are, and that comes from up here in the statement itself. So respectively, it went 23, 38, 34, and 24. A total of 119 people. So for my expected counts, if I have a total of 119 people and I want that to be expected to be usage being consistent, that means all stalls should have the same number of people. So it's 29.75 for each stall. When you are expecting equal usage across any certain number of categories or cells, you simply are going to take the total number of counts and divide that by the number of cells. Oftentimes you're going to have actual percentages that you're going to deal with, and therefore you'll do the percent times the total. Do not round, or if you do round to 2 decimals, but do not round to an integer, because our expected cells aren't saying I'm seeing 29 3/4 of a person using a restroom. This is just where we can expect the numbers to fall. Now, to be able to go through this, we need to put our information in lists in order to calculate this the easiest way possible. So what I do is I'm going to put this into list 1, this into list 2, and I'm going to calculate my components in list 3. Now the component, this is the observed minus the expected squared all over the expected. And when we're talking in terms of my lists, that means it's going to be observed is in list 2 minus list 1 squared divided by divided by list 1. So let's go ahead and put our data in. So in my stats, I'm going to do 29.75. Oops. 29.75 for each row. List 2, my observed, 23, 34, helps if you type them in right, 38, 34, and 24. Then my favorite thing about these calculators is the ability to do multiple tasks just using a formula. So I'm going to put parenthesis, list 2, right there, minus list 1, squared, divided by list 2. Now I'm actually going to record these numbers. So I have 1.981 1.791, .531, and 1.378. Now, in order to finish with my computations here, there's a little bit of work that I need to show so that I make sure that I talk about everything. The first thing is we have our expected cell counts are all greater than 5, and you can physically see that on the table. If you have shown that on the table, just making that statement is perfectly fine. So what we're going to say now is that with our conditions met, we have no distribution. This time we're not going to say assume normal or assume t-distribution. We're just going to say we're going to do a chi-squared goodness of fit test, and here we really should say how many degrees of freedom we have. The degrees of freedom is equal to the number of rows minus 1. So in this case, that is going to be 3 degrees of freedom. Now when it comes down to the actual work that you have to show for your mechanics, you have to show how we calculate our chi-squared statistic. The chi-squared statistic is taking each of these numbers and adding them together. But not just that, it's showing where we came up with this. So we're going to say the chi-squared statistic with 3 degrees of freedom is found by doing, and we must do at least 2 of these components, show where the calculations came from. So we're going to write observed minus expected squared over expected plus, do it again, the next one, observed minus expected squared over expected. And then you're just going to do plus dot dot dot. We need to find out what that value is. The easiest way to do this is to go back to our calculator, understanding that all of my components are in this list 3. So I'm going to go to my general menu, and I'm going to say, it's under a list, so second stat to get to my list. And under math, I want the sum option. And I'm going to take the sum of list 3. And each of your lists are second and then 1, whatever list it's found in. That value is 5.68. We're going to round it to 2 decimals. To make my life easy, I'm going to store that as x. So 5.68. And our last step that we need to find here is what the actual p-value is. So we're going to say the probability of finding a chi-squared component of 3 degrees of freedom. This is always greater than, and the chi-squared statistic was 5.68, is equal to, and then what we're going to do here is we're going to go to second vars. We're looking for a chi-squared CDF, not PDF, continuous density function. Now for chi-squared, even though they give us the option of a lower and an upper, we're only going to be talking about going from my statistic to infinity. So we're going to do from 5.68, or actually from x, because remember I stored that. Now, believe it or not, this actually does have a limit to how many 9s you can put in before it gives you an error symbol. So I'm just going to do 9,999 with 3 degrees of freedom. And so I get basically 0.1282. And just so that you know, please do not write down the calculator speak when you are writing your answers, but I want you to be able to reference the formulas that are used for this. So the formulas used for a chi-squared test statistic here, this was chi-squared CDF from whatever that x was to 9999 with your degrees of freedom. Okay, but again, we don't really include that. You want this notation here. So making our conclusion, with our p-value of 0.1282 being greater than alpha, where we're sticking with our 0.05 alpha here, we fail to reject the null. We do not have enough evidence to support the claim that the bathroom stall usage is not consistent across the 4 stalls. Okay? Just want to be very careful with that. I know it sounds a little bit weird. We do not have enough to say that it is not consistent, but we cannot say that we have enough to say that it is consistent. So don't cancel out your double negatives there. Okay? It's all right to have what we have. So in a chi-squared test for any of them, you want to make sure that you clearly identify your null and alternative hypothesis using sentences clearly describing the context. Your assumptions and conditions include the fact that the data is counted and what those counts represent. The independence assumption is going to be there for our goodness of fit and our homogeneity tests, but not for our independence test. We want to talk about randomization or a representative sample. And you want to show, not just mention, but show what all of your expected cell counts are. When you make your statement, please be sure to include your degrees of freedom. When you're calculating your chi-squared statistic, you actually have to show how those are calculated. Make your statement for your p-value, and then your conclusion. Now in this case, we didn't find enough evidence to reject the null. Had we found enough evidence, we would look back at our chi-squared test statistics, chi-squared components, and identify which number was the largest. For example, in this case, my component that is the largest does in fact come from the first restroom, and that restroom does show that usage is below what we would expect, but it's not because that component is somewhat small, it's not abnormally below. But we would incorporate that if we rejected the null.